Well, hello, good people. Today we are talking about time dilation, the twin trip, and time travel. Before we do, we need to review the two postulates of special relativity. The first postulate of special relativity says that all laws of nature are the same in all uniformly moving frames of reference. This is going to quickly become very, very important to us as we discuss our topics of the day. It means that you can't tell if you're in a moving box or if you're in a still box if you're moving at a constant velocity. All the laws of nature are completely the same whether you're moving or still, and all motion is relative. That's the first postulate of special relativity. The second postulate of special relativity says that light always travels the same speed at a speed of c regardless of the motion of the source of the light or the motion of the observer. It's this weird rule that light doesn't seem to adhere to the principles of relativity or of reference frames, but that light always travels the same speed c regardless of your reference frame. These two postulates will assist us today in the story of the twin trip. Now here's something that we did not know for quite some time. Wait. This, as you know, is Pfeiffer. And you know all about Pfeiffer's history, about her time in California when she would build cars and drive them along the coast. And you know all about her engineering parents and how she was very lovingly adopted by a very kind family. She had great parents and a great childhood. But you know that she never really knew... Sorry, it's a sensitive topic. She never really knew very much about her species or where she came from. It's kind of ambiguous. Is she a chicken? Is she a bird? Kind of hard to say. So she never really grew up knowing much about that or talking much about that. It's a little bit of a sensitive topic for her. But in general, her childhood was very, very happy. But it was not until Pfeiffer became much older that one day, as she was walking through the park, she looked up and she saw there, on the path of the park, quite serendipitously, another creature, much like herself. As he was walking down the path, he looked up and he saw her. And he thought, I've never met any creature similar to myself. So without even knowing who each other were, they ran towards each other. And they said, who are you? And she said, who are you? And they both talked to each other back and forth. And they found out that as they were the only two members of their species, that they were in fact related. And they were in fact twins. They had come from the same family some time before, but then were separated at birth and adopted by two different sets of parents. Pfeiffer was adopted by parents in California, and Mr. Pfeiffer was adopted by parents in Britain. And he grew up a very good British gentleman. Well, he had gone to a tour. He had gone to America to get a good tour of the art museums there, as he had studied art in Britain and wanted to see some of the American museums. I don't know why you'd want to see some of the American museums when you could see some of the European museums, but anyway, that's what he was doing there. And so they were both walking through this path, enjoying a very beautiful day, when they just so happened to run into each other. And you cannot imagine what a happy day it was for the two of them, as they both talked about their lives growing up, talked about the struggle of being the species that they are. Pfeiffer talked all about her time riding on the cliffs of California and building cars. And Mr. Pfeiffer, as he says because he's British, Mr. Pfeiffer told all about his time studying art, and it was a really, really beautiful moment for both of them. Well then, Pfeiffer got a call, right in the middle of their conversation. Pfeiffer picked up the phone and said, hello, is this very important? Because I'm in the middle of probably one of the most important meetings of my whole life. And the person on the phone said, yes, actually, this is very important. And Pfeiffer said, oh, what's happening? And the person on the phone said, we have an opportunity for you, but you have to act right now. They said, we're trying an experiment and we're testing an experiment to see if we can travel all the way to the center of the galaxy. Pfeiffer's little bunny ears perked up. Pfeiffer said, interesting. You see, Pfeiffer grew up as an engineer and a good physicist. And so she said, this is actually kind of the perfect job for me. I've been building cars since I was 6 years old. And so Pleafer, after talking to them for about 3 minutes, decided that yes, she was determined to be a part of this experiment, and she wanted to help all of creature kind make it to the center of the Milky Way galaxy. So she finished up her conversation with Mr. Pleafer, and she said, Mr. Pleafer, because he's British, it is so very nice to meet you, and what a joy it is to get to be reunited with my family, but I have an opportunity that I must take immediately. And Mr. Pleafer said, I totally understand, Pleafer. It is so very happy to see you, but I shall see you once again when you get back. Then, at that very moment, a spaceship came to pick up Pleafer. Pleafer boarded into the spaceship, said goodbye to her newly found family, and started zooming away. Now, in order to get to the center of the Milky Way galaxy, you could imagine that Pleafer would have to travel very, very fast. We're talking like close to the speed of light type fast. So here's what they did, is they put Pleafer in this rocket ship, and they accelerated her at a speed with an acceleration of 9.81 meters per second squared for a little less than a year. If you're accelerating at 9.81 meters per second squared for a little less than a year, well, you can really get going pretty fast. And 9.81 meters per second, you know, is the acceleration that we daily experience due to gravity. So it's not an acceleration that's too hard on your body. Actually, I'm going to go right here for a ship. It's not an acceleration that's too hard for your body. It's absolutely something that you could manage. Now, one day, as Mr. Pleafer was walking through the park about a year later, a little less than a year later, he looked up into the sky and he saw that overhead, oh gosh, that is going to be way too large. Let me try again. This is a rocket ship. There's fire coming out the back. Okay. You can't really see the fire. That's kind of disappointing. But anyway, okay, up ahead was... Oh, we got an announcement. Up ahead in the sky was Pleafer. And as Mr. Bubbles looked up, he saw... Here's Mr. Bubbles.
It'll be up to you if you'd rather go to the music room or have them come up. So please give me a call.
Here is Mr. Bubbles. And you can tell that it's Mr. Bubbles because he has a great hat, which I'll draw in a second. Meanwhile, Pleafer was up here, going very, very fast. Here's Pleafer. Oh, wow, that is awkward. That's not what her nose looks like. Okay, there's Pleafer. And Pleafer looks down at Mr. Pleafer and says, "Hi, Mr. Pleafer!" Except she says it British, of course, because he is British. Here's a little hat for him. Wow, lots of announcements for today. You are just really blessed to get to hear a lot of real-time stuff that's going on. Okay, so Mr. Pleafer looks up and sees Pleafer, and Pleafer says, "Hello, Mr. Pleafer," and Mr. Pleafer says, "Hello, Pleafer," and Pleafer goes zooming past very, very fast, very close to the speed of light. Well, it turns out that in order to keep track of time during her travels, Pleafer has a very, very special clock inside her spaceship. And her clock looks something like this. It's a clock that is made up of, essentially, mirrors and light. And here's how her little clock works. Her clock is made up of 2 mirrors, one on the top of the ship and one on the bottom of the ship, like this. Now, between those 2 mirrors, a ray of light passes, and the mirrors are perfectly spaced apart so that the amount of time it takes for light, you could imagine like the amount of time that it takes for light to bounce down and back up again would be something that would be very controlled. Like, for example, you could make it so that your mirrors are half a second apart each. So it takes half a second for the light to go down and then half a second for the light to go back up again. Although that would make for a very, very big spaceship and quite impractical design. So it's a little bit less than that, but you could imagine that the light is bouncing back and up every time. And it takes a certain amount of time for the light to bounce back up. And that's how Plifer is keeping track of time, is basically by counting the number of bounces of the light. And if each bounce, like an up and a down, takes 1 second, then for every time it takes a little loop, then you get 1 second worth of time. So that's how Plifer is keeping track of time. Now, as Plifer's little ship here moves forward, Mr. Plifer is watching from the ground. And here's what he sees. He sees that Plifer's ship moves from here to here in a certain amount of time. Now, here's what's very interesting. Let's draw Plifer's clock in here again. Here's Plifer's clock. And of course we will draw Plifer again. Yes, of course we are using all the colors, because it would be inaccurate to represent Plifer with some other colors. I keep drawing that. It's not a smile. I should know by now. Okay, there we go. There's Plifer, looking great. Okay. Now here's what Plifer sees. Plifer sees that her light is bouncing back and forth, up and down and up and down and up and down. And Plifer is in an inertial reference frame, or a frame of reference which is moving at a constant velocity, some velocity v. And so as she's going up and down, she watches the light go up and down and up and down and up and down, just like this. Just like you would if you took a bouncy ball and you threw that bouncy ball up and down. But that's not what Mr. Plifer sees. Because Mr. Plifer, when he looks at the light, he sees that the light goes down, and then on the way back up again, it travels up as the ship is moving forward. So while Plifer sees the light just go straight up like this, Mr. Plifer sees the light go up at a diagonal. Oh, whoops. I can do it better. He sees the light go up at a diagonal. He sees the light go up at a... Oh, okay. He sees the light... The distress. Can you hear the distress? Okay, there. That's not too bad. He sees the light go at a diagonal, like this. And so what he'll see is he'll see the light go up at a diagonal, then back down at a diagonal, then up at a diagonal, and then back down at a diagonal. Meanwhile, Plifer just sees the light going up and down and up and down and up and down. Which one's right? Yes, they're both right. They're just seeing it from different perspectives. But here's what gets weird. Sorry, let me erase my lines here. Here's what gets really weird. Is that Plifer sees the light traveling at a speed c, and Mr. Plifer also sees the light traveling at a speed c. Well, check it out. We'll do two different colors. We'll do one for Plifer and one for Plifer. I'm going to do light pink for Plifer, and then we'll do this brown color for Mr. Plifer. Okay, so here's what Plifer sees. Plifer sees, wait, sorry. You can do it. Okay. Plifer sees that her light is going to travel down a distance, delta x. We'll call it delta x naught is the distance that her light travels, delta x naught. Meanwhile, Mr. Plifer is going to see that the light travels a distance of, we'll call it x, where these two distances are totally different. In this amount of time, Plifer's ship travels a distance, a distance like this. Travels a distance of, we'll call it d of the ship, the distance that the ship goes. So, Plouffer sees the distance that the light travels as being different than what Mr. Plouffer sees for the distance of the light. Yet they both see it going at the same speed c. Here's what's weird then. We know that speed is equal to delta x over delta t. That's common knowledge. Well, both Plouffer and Mr. Plouffer are going to say that they see the light traveling at a speed c. But for Plouffer, that speed c is going to equal a little x naught, delta x naught, divided by a little delta t naught. Meanwhile, for Mr. Plouffer, he's going to see that light goes a distance x, I forgot my deltas, a distance delta x over an amount of time, delta t. Well, check this out. They see the light as going different distances, but c still has to be the same. So in order to keep c equal, if delta x naught is very small, delta t naught has to be very small. But for Mr. Plouffer, if he sees a bigger delta x, if he sees the light as traveling a greater distance, in order for that light to still be traveling the same speed c, he would have to see it as taking more time. Here's what that means. It means that the amount of time that it takes for Plouffer's clock to go down in her perspective is less than the amount of time it takes for the light to go up or to go down in Mr. Plouffer's perspective. So Plouffer sees the light go up, and when Plouffer sees the light go up, it takes, let's say, half a second. But when Mr. Plouffer sees the light go up, it takes longer than a second. This is strange, because the implications of this are, as you might imagine, quite weird. The implications say that time is different for Plouffer and for Mr. Plouffer. They are actually experiencing time differently. And it's not just the light clock, because some students say, oh, well, that's just because the clock is made out of light. But that's not true. It's actually everything else. When Mr. Plouffer is looking at Plouffer, he would see the clock moving slower or taking more time for the light to hit each panel. But if he could see Plouffer's heartbeat, he would also see Plouffer's heartbeat as beating slower. If Plouffer was making herself a bowl of cereal and she took out the milk to pour it into the cereal bowl, Mr. Plouffer would see the milk pouring slower. When he looks up at Plouffer, he would see that everything that Plouffer is doing is in slow motion. And so, when Mr. Plouffer looks at Plouffer's life, Mr. Plouffer says, Plouffer, your life is in slow motion. Your time is all stretched out and slow. But to Plouffer would say, no, my life is normal. And she would pour the milk into her cereal bowl, and it would do exactly the same thing as it always does. It would always pour the same way. And so, they experience time differently. Now the question is, who is right? Is there a contradiction here? Is
Let me know if you
Mr.
can help or
Plouffa's
to.
view of
Thank
Playfair's
you.
time right, or is Playfair's view of Playfair's time right? The answer is yes. Both are true. They both experience time correctly, and both are true and not contradictory. You'll remember this from our last video. Do you remember if I throw a baseball at a speed of 40 meters per second while I'm on a truck? Someone else would say that baseball was going, or sorry, not 40 meters per second. Wow, that would be insane of me. That would be so very cool. I would be so impressive. No, but if I threw a baseball at 40 miles an hour on a truck, and that truck was going 40 miles an hour, someone else would say that the baseball was going 80 miles an hour, and I would say that the baseball was going 40 miles an hour, and we would all say, yeah, okay, that's fine. That all works out. That all makes sense. Yes, both stories are true. It just depends on where you're standing. Same thing here. It feels weird because it's time, but it's the same thing. If I asked you which story is true, whose time is correct, you would say, yes, both times are correct. Playfair experiences time going just like normal. Mr. Plouffair, when he looks at Playfair's time, sees time going slower. And both are right. But now, check this out. To Playfair is actually totally still. To Playfair, she's pouring her milk into her cereal as normal. If she wants to play a game of cards, a game of like solitaire or something, she can play solitaire all by herself and all the cards will stay on the table. She says, to me, everything is normal. When Playfair looks out the window, to her, it looks like the whole earth is going backwards like this. And so, if Mr. Plouffair, I gotta say his British name. If Mr. Plouffair had his own light clock down here, made up of mirrors, the same way, well then, Plouffair would see Mr. Plouffair's light clock as going down and then up, and then down, and then up, as she watches the whole earth travel backwards. And so, from Playfair's perspective, she would see the exactly the same thing as what Mr. Plouffair is seeing about her. When she looks at Mr. Plouffair's clock, she would see that his clock, it is really hard to transition between the British accent and the not British accent. She would see that his clock is going slower than her clock. She would say, my clock is going normal, but his clock is going slow because the light has to go zigzaggy as the earth moves backwards. Then she would say, interesting, it also appears that his heartbeat is beating slower. If Mr. Plouffair were to pour a bowl of cereal, Plouffair would see that milk is very, very slowly coming out of the bottle. And so, Plouffair looks at Mr. Plouffair and says, your time is slowed down. And Mr. Plouffair looks at Plouffair and says, your time is slowed down. Who's right? Yes, both are right. Remember the two ships passing each other. And one ship says, you're the one that's moving. And the other one says, no, you're the one that's moving. I'm sitting still. And they're both right. It just depends on your perspective. Here's what this shows us. This shows us that time is not a constant. Not everyone travels through time the same way. The same way that not everyone travels through space the same way. What links space-time together is speed. If you're going a certain speed, you can actually change the way that you navigate through space-time as you change your delta x and your delta t. Speed is relative, but time is also relative, and as we'll see soon, length is also relative, or your distance traveled is also relative. There is only, as it turns out, one real constant, one real thing that stays the same, and that is light. Light is the only constant in the universe, and everything else revolves around it. Let's take a look at a little derivation. I am going to go ahead and pull up another screen, and then we'll show you a little derivation real quick. And I'm wondering if there's a way that I can keep... Actually, you know what I'm going to do? I'm just going to erase this stuff here, and then we're going to use this because this little setup right here is going to be helpful for our derivation. So 1 second, I'm going to clear some things out, and then we'll do a little derivation. 1 sec. Okay, so here we go. Let's take a look. Here we have, you can see a very, very nice right triangle. Do you see it? This is the distance that the light travels in Pfeiffer's frame of reference. This is the distance that the light travels in Mr. Pfeiffer's frame of reference. And this is the distance that the ship travels, making a very nice triangle that looks something like this in an equation. We can say, actually, I'm going to move it up a little bit because I got a lot of stuff to fit in space. Oh, gosh, wait, redo that. Okay, here we go. We can do it. Yes, perfect. Okay. Here's what's true is that, and I'm going to change my colors up here, which is going to be a lot of time, but it's so worth it. Oh, and I lost my delta again. Okay. Here's what we can say is true, is that delta x squared is equal to delta x naught squared plus the distance the ship travels squared. Wait, let me try it. Hang on. Okay. Delta x naught squared plus whoops, hang on. You guys like already have this thing written down. Oh no, redo. Plus the distance the ship travels squared. Okay. Ooh, sorry, it took only about a gazillion years to write that down. Well, we also know that v equals delta x over delta t, so we could rearrange this here, and for the rest, I'll just go gray. We could rearrange this here to say that delta x is equal to v times delta t. That would mean that the distance the light travels in Mr. Pfeiffer's frame of reference is equal to c times the time that it takes in Mr. Pfeiffer's frame of reference. Then, for this little x naught here, that is c times the time that the light takes in Pfeiffer's frame of reference, plus the distance the ship travels. The distance the ship travels is the speed of the ship, times the time that the light takes in Pfeiffer's frame of reference or in Mr. Pfeiffer's frame of reference. Well, we would say that we would go with the time that it takes in Mr. Pfeiffer's frame of reference. Because in Pfeiffer's frame of reference, Pfeiffer isn't even moving. So the distance of the ship is like a senseless way of talking. There is no such thing as distance for the ship because the ship isn't moving. So Pfeiffer would say there is no such thing as the speed of the ship. But Mr. Pfeiffer would say, yes, this ship does have speed and it takes a time delta t for the ship to move from here to here. Now, from this point forward, I'm going to do a little bit of algebraic rearranging. First, I'm going to get delta t by itself, or delta t not by itself, and my eventual goal is to get delta t by itself, but we're going to develop two equations. Let me show you what it looks like. Here's what we do. The first thing I'm going to do is I'm going to try to get this delta t not by itself, so I'm going to move everything over to the other side. I'm going to get c delta t, all of this, squared, minus the speed of the ship times delta t, all of that, squared, is equal to, sorry, I'm going to try to write small here so that I can try to fit everything in, c delta t naught squared. Well, here's what we could do next is we could take that little squared and we could distribute it. So we'd get something like, whoa, wait, let me try this again. We'd get something like c squared delta t squared minus v squared delta t squared is equal to c squared delta t naught squared, like so. If I'm trying to get this delta t naught all by itself, I can divide both sides by c squared. like this. And then we'll see that some stuff is going to cancel out here. I'm going to get, and I'm going to move my box here. Sorry, box, go up. Yay. Okay. I'm going to get, boop, doop, doo. Oh, nope, not that. Sorry, Playford didn't mean to put my math inside your spaceship. Okay, I'm going to get, first, this c squared over this c squared here, those two terms are going to cancel out. So I'm going to get delta t squared minus v squared delta t squared all over c squared, because those won't cancel out, is equal to delta t naught squared. Next, I can pull out this little delta t squared because it's in both of these terms. So I get delta t squared, pull it out, of 1 minus v squared over c squared is equal to delta t naught squared. And then I can square root both sides like this. And if I square root both sides, I get delta t times the square root of 1 minus v squared over c squared is equal to delta t naught. And my very last move here, I'm actually going to rearrange this thing and solve it for delta t, and I'm going to draw right here an equation that looks like this, that delta t is equal to delta t naught divided by the square root of 1 minus v squared over c squared. And this equation right here is what we call the time dilation equation, because it shows the way that, wait, go back, undo. It shows the way that time gets dilated, that time looks different depending on your reference frame and the speed of your reference frame relative to another reference frame. As you write down this equation in your bag of tricks, can you please make a note to yourself? Here's our time dilation equation. Can you please make a note to yourself? What is delta t? Whose time is that representing? It's who looking at who. What is delta t naught? It's whose time looking at who. And what is v for? Make a note in your notes. The truly trickiest thing about this equation is that students don't know which delta t stands for what. Delta t naught, that refers to Pfeiffer's time looking at Pfeiffer's own clock. Delta t naught is Pfeiffer looking at Pfeiffer's time. It's Pfeiffer's time in her own reference frame. Delta t is Mr. Pfeiffer's perspective of Pfeiffer's time. Its delta t here corresponds to our delta x, which is the distance that Mr. Pfeiffer saw Pfeiffer's ship travel, or the light from Pfeiffer's clock travel. So what you can see here is delta t, this guy right here, always refers to the outside observer looking in. Delta t naught always reserves to the time for the person looking in their own reference frame, the time that the person experiences of themselves. Delta t is the time that somebody on the outside experiences looking at the person. Let's try a little bit of a practice problem. I'm going to get a new page pulled up here. Okay, suppose that a clock goes whizzing by your face, and this clock goes whizzing by your face with a speed of 90% of the speed of light. That is, wow, a crazy, crazy fast clock. Actually, let's give ourselves 3 sig figs for funsies. Here's a question for you. How long would you see it take for the second hand to make one tick on that clock? Stop here and start by thinking about, what are you solving for? Are you looking for delta t? Are you looking for delta t naught? here's what you're saying. You're saying, okay, I'm looking for how much time I'm going to see for that clock. I'm the outsider looking in, so I'm looking for delta t. The clock experiences this tick of one of its second hands as taking 1 second. That's the amount of time the clock experiences in its own reference frame. Now we're ready to go. We start with our original equation, that delta t is equal to delta t naught all over the square root of 1 minus v squared over c squared. We're already rearranged in terms of what we're looking for, so we're all good to plug in numbers. Let's go ahead and try it. The time that the clock experiences for the tick of 1 second hand is 1 second, so I'm going to plug in 1 second there. Then I see the clock as moving at a speed of 0.99, 0.900, times c, the speed of light. We'll square that term, and we'll also square our c in the bottom. Hey, notice there's a little bit of simplification that you can do here. Check it out. Couldn't we just rewrite this as 1 second divided by the square root of 1 minus 0.900 squared times c squared over c squared. Our c squareds cancel out, and then when we type this into our calculator, we just have to do 1 divided by the square root of 1 minus 0.9 squared. Plug that into your calculator, and you would get 2.29 seconds with 3 sig figs. So you would see 1 second on the clock as taking 2.29 seconds. To the clock, it only takes 1 second, but to you, 1 tick takes 2.29 seconds. Which one is true? Yes, both. They're both totally and completely true. Time is relative. It depends on your frame of reference. Now, I want to actually talk a little bit more about this equation, so I'm going to go ahead and get it pulled up for a second, because I really want to take a look at this equation and look at all of its implications. So I'm really just going to I'm going to pull up a separate little tab here, and I want to look at this equation that we've been talking about, the time dilation equation, which says that the amount of time that you experience. Oh, wow, that was just dramatic. Okay, let's try this. Square root of 1 minus v squared over c squared. Okay, perfect. Now here's what I want you to see. This equation is crazy because this equation suggests that time is relative, which is kind of a crazy suggestion. So in order to see if we're even willing to accept this new theory, we have to check the correspondence principle. In other words, does this equation correspond to things that we already know are true? Newton's laws seem to be working pretty well. So if this isn't corresponding to Newton's laws, we got some issues. Also, we've noticed some things in our daily lives. For example, if I got in a car right now and I started driving away, would the clock on my computer, if I left my computer here, would the clock on my computer count seconds differently than the clock in my car? This equation says, yeah, they would count seconds differently. They would disagree about how much time was a second, according to each other. They would say, we see time differently. But what doesn't happen to you most of the time is you don't get in your car, drive someplace, and then get there and say, oh guys, so sorry I was late. It was just, that whole time dilation thing. I was in my car moving. My car's clock is totally different than your clock since we were in different reference frames. You know how it goes. That doesn't happen. We found that in our daily life, time seems to be pretty consistent whether you're in a car or sitting in the park. And so, for that reason, we want to check the correspondence principle. That is a result, that's an observation that we see all the time. Is that actually true? Well, check it out. Do you see how here, this v here is v squared divided by c squared? Do you see how if this v is going to make a dent in this equation at all, it's got to be something for serious big. If that v squared is something small, even something small squared all over c squared, well, that's basically going to be 0, essentially. And so what you'll essentially get here is that for any speed that's not really that big compared to c, like I'm talking like your car driving down a highway. Your car driving down a highway is going pretty fast, but it's not going anywhere near the speed of light. For what we call non-relativistic speeds, very slow speeds, this whole term essentially becomes 0, which means this ends up being 1 minus basically 0, which means it basically ends up being the square root of 1, which means it's basically like delta t is equal to delta t naught divided by basically 1. So most of the time, correspondence principle, most of the time in your daily life, this delta t here, the delta t that someone else outside of the car experiences, and the delta t that you in your car experience are the same. Are they slightly different? Yes, but noticeably different? No. It's not until we get to really, really fast speeds that this v starts to make a dent in the equation. So we say, according to the correspondence principle, looking at this thing, we say, yeah, okay, that looks like that could correspond to real life, because the results that it gives are actually the same as the results that we get in our real, everyday, ordinary lives. So that seems to look good. Now, here is another implication of that. Another implication is what happens when you start going really, really fast. Well, let's start like if you just started going fast, like something close to the speed of light. If you were going something close to the speed of light, then you would get that delta t is equal to delta t naught all over the square root of 1 minus v squared over c squared, like this. If your v squared was worth something, then you would get delta t naught divided by the square root of 1 minus something here. Check this out. If I rearrange this equation a little bit, I'm going to rearrange to solve for delta t naught. I would get that delta t naught, and I'll show you what the whole point of this is in a second. Delta t naught is equal to delta t times the square root of 1 minus something, which means you would end up with delta t times something small. In other words, time would shrink. Here's what I want you to see here. For a long time, we thought that it would never be possible to make it to the center of the Milky Way galaxy in our lifetime. The reason why is because the center of the Milky Way galaxy is about 26,000 light years away. It's 26,000 light years away. What we've always thought is like, well, okay, that is great. That's a very far distance. But even if we went the speed of light, we would never be able to make it to the center in our lifetime. Because even if we went the speed of light, it would take us 26,000 light years to get there. And no one can survive for 26,000 light years. That's just on the way there. If you wanted to make it on the way back, you'd need another 26,000 light years. But here's the thing. If you started going really, really fast, you would experience time differently than the time of people on Earth. This delta t would be the time that people on Earth experience you as taking. So they would say you are taking a longer time. But notice, you multiply their time by the square root of 1 minus something if you're going very, very fast, and you get the time that you would experience would be much, much smaller. So in Earth's frame of reference, if you took 26,000 light years to get to the center of the Milky Way galaxy, you would experience that time, if you're going very fast, as taking much less time than that. So it's actually feasible that you could make it to the center of the galaxy in way significantly less than 26,000 light years if you were going fast enough. The people on Earth would still say that it took you 26,000 light years, but you would not say that it took you 26,000 light years. You would feel as though it took you less. And so it would actually be feasible to go to the center of the galaxy, but by the time you get back, 2 sets of 26,000 light years will have passed on Earth for for as much time as it took you to be there. So, yeah, so that'll be slightly different for you, but that's the general idea. Now, I want to talk about what happens if you start to go really, really, really fast. Like, what if you actually were the speed of light? Or, in other words, what would light experience? Well, to see what light would experience, let's look at the delta T naught. That is the time that light experiences in its own frame of reference, times delta T, that is the light that we experience light taking. And that's going to be multiplied by 1 minus c squared over c squared, because light travels at a speed c. Looking at this equation, what you see is that you get 1 minus c squared over c squared. Well, c squared over c squared is just 1. And 1 minus 1 is just 0. So you get that the time that light experiences is equal to 0. Here's what that means. That means if I said, hey, light, it looks like it took you a time t to cross the room, to get from over there to get to me. Looks like that took a time t, delta t. The light would say, no, 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 no. In my frame of reference, that took 0 time to get from there to there. The light would say, I would say, light, you took time to get places. The light would say, no, 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 I was already there. The light would say, I'm outside of time. I've always been there. And I always will be there. Because light is outside of time like this, in light's frame of reference, light is eternal and omnipresent. It is everywhere in space, in no time. And so while we say, light, you took time to get here, light doesn't say that. Light says, I was already there and I always have been there. And so light, in light's frame of reference, is a whole different ball game, totally different thing. Now, before we can finish out this lesson for today, we actually have to check back in with Plefer and Mr. Plefer, because they have some weird situations that are going on. So I'm going to go ahead and head back to their slide. 1 second. Okay. Wow, I am glad I paused that, because that only took like 5 gazillion years to fix. You guys have no idea what I just went through. Anyway, okay. So back to Plefer and Mr. Plefer. Here's a question for you. We have this interesting thing where they are each experiencing time differently. Now, here's the question is, who is aging faster? Plefer or Mr. Plefer? The correct answer is the same. Because Plefer says, I'm not really moving. I'm in an inertial reference frame. I'm moving at a uniform rate, which means that everything for me is the same as it always is. That's the first postulate of special relativity. Plefer would say, my heart is beating the same speed it always does. Plefer would say, the milk that I'm pouring into my bowl of cereal pours out at the same rate it always does. Everything in my life is the same as it always was. She would say, Mr. Plefer, it's you who is going backwards. You are the one who is moving. I am still, and the whole world is zooming off, going the other direction. That's what Plefer would say. Meanwhile, Mr. Plefer would say, no, 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 no. I'm the one who's still. It's my heart that's beating normal. And you're the one who's going fast. And you're the one whose heart is beating slowly. Which means both of them would experience time the same way. They would both experience time as completely and totally normal to themselves. And they would both be progressing through time similarly, in the exact same way as the other twin. However, something weird happens, not when Plefer is moving at a constant velocity, but when Plefer accelerates. You know how when you're in a car, if you slam on the brakes, you can feel it. But if you're going at a nice constant speed, you can't really feel that. You're in an inertial reference frame. But if you slam on the brakes, you can feel that. You have a sudden lurch forward. And if you step on the gas pedal, you get sucked back into your seat. You lurch because of the acceleration. Well, it turns out that when you accelerate, you don't only lurch in space, but you also lurch in time. You experience a lurch in time. Now, you can't feel it the same way that you can feel the lurch in your body physically when you accelerate, but you do lurch in time. Anytime you accelerate, there's a little derivation that we're not going to do in this class because it's a little bit of a slippery, sneaky kind of equation, and it's a little bit of a tricky derivation. So we're not going to do it together, but here's what you need to know, is that anytime you accelerate, time lurches and it slows down. Anytime you accelerate, time slows down. Anytime you accelerate, time slows down. In order to take this whole journey, Plifer accelerated twice. Plifer first accelerated to get going in the first place, to get going up to a very, very high speed. But then Plifer also, if Plifer ever wants to rejoin Mr. Plifer back on Earth, Plifer will have to accelerate again, slowing down in order to be with Mr. Plifer again. So that is 2 accelerations. In both of those accelerations, Plifer's time slows down. Her clock actually physically gets slower. Meanwhile, Mr. Plifer, back on Earth, is not accelerating, and his clock keeps ticking forward as normal. Which means that when Plifer gets back, Plifer will be younger than Mr. Plifer, because Plifer accelerated, and in those accelerations, her time slowed down in comparison to his. Now, in order to have this kind of difference in time, you actually really do substantially have to accelerate. So you really have to be changing your speed like a lot. Now, if you went something like, like 99% the speed of light, and you accelerated up to 99% the speed of light, and then you slowed down again, and let's say that you were traveling at the speed of 99% the speed of light for 1 year. If you did that for 1 year, 1 year to you would equal 7 years to the person who never accelerated. Let's say that you accelerated a little bit more. So now you got up to a speed of 99.9% the speed of light. At that speed, because of your accelerations, if you traveled at that speed for 1 year, between the 2 accelerations of you speeding up and then you slowing down again, those 2 accelerations would cause 1 year of your life to be 70 years for the person back on Earth who did not accelerate. And if you accelerated up to 99.99% the speed of light, and you did that for a year, your 2 accelerations, both speeding up and slowing down, would make it so that 1 year of your life would equal 200 years of everyone who didn't accelerate. You don't actually have to get in a spaceship to do this, because all you have to do is accelerate to travel in time. If you wanted to travel in time, what you would do is you could get inside of a really big spinny thing. And if you get inside of that spinny thing, well, spinning is acceleration because you're constantly changing your direction. As you constantly change your direction, you're constantly accelerating. Hang out in that little spinning thing for a little bit. When you get out, you'll be dizzy, and everyone will be older than you, because you spent time accelerating, so time was slower for you than it was for everybody else. That is a way to travel forward into the future. But because time only slows down when you accelerate, there's no way to travel back into the past. You can make time slow down for you, but you can't make time speed up for you in a way that then you're going back in time for everybody else. You can only make time go slower, but time always travels forward. That you can also see in our other equation if you take a look at it. Do you see how? Wait for it. It's going to load way faster this time. It's going to be awesome. Wait for it once again. Okay, check out our time dilation equation right here. Whoa. Let me try again. Okay, here's our time dilation equation. Check it out. Do you see how time will always slow down here and never... you can never make your time go negative or go backwards. Here's what I mean by that. Do you see how if it's 1 minus 1, the best you can get to here would be like 0-ish? And so then the biggest thing you would get to here is a really big number. There is no way to get to something where you're going actually where this number this is a smaller number than this number. That is not possible. So it's not possible for the person who's observing you to see that you are going faster than you actually are. This means that there's no way to go back in time. There's also no way to go back in time because of the second law of thermodynamics. The second law of thermodynamics says that we are always constantly increasing in entropy in the universe. To go back in time, you would have to decrease entropy. Eggs around the world would have to get uncracked and remold themselves. And probabilistically, it's not possible for the egg to go back together like this again after it has already been separated. Because entropy is always increasing, you can't go back in time. So both special relativity and also the laws of entropy say that time travel backwards in time is not possible. But you could time travel forwards in time if you're moving through time at a slower rate than other people through acceleration. And that is pretty much everything that we have for today. When I see you next time, we will be talking about length and mass and how length and mass are also relative. And that's all for today, folks. I hope you have a wonderful rest of your day. Bye, good people.